Okay, so what if I told you an AI could autonomously conduct a high-energy physics experiment, literally freeing up years of human labor? It sounds completely like science fiction, right? Well, today we are looking at a paradigm-shifting paper that proves this autonomous capability is absolutely not sci-fi anymore. It is happening right now. Welcome to The Explainer.
Let's dive right into this. To truly appreciate the stakes here, we really have to understand the grueling reality of experimental physics. Discovering the fundamental building blocks of our universe is incredible work, but the day-to-day process? It is a massive, exhausting, years-long endeavor. We are talking about endless late nights, wrestling with legacy software, digging through thousands of lines of code, and battling endless bugs just to process a single dataset. But this painstaking reality might have just found a revolutionary solution. So, here is our roadmap for the explainer today. First, we'll look at the physics analysis bottleneck we currently face. Then, we'll meet the JFC framework. After that, we'll check out the team of AI agents doing the heavy lifting, discuss the critical human unblinding gate, and finally wrap up with the profound implications for the future of research.
All right, part 1, the physics analysis bottleneck.
To put it simply, modern particle physics is just totally bogged down by boilerplate code. The sheer contrast we're talking about here is staggering. In the current world, an experimental physics analysis spans the vast majority of a graduate student or postdoc's time. They spend a year, sometimes way more, writing thousands of lines of structurally similar code to process data, constantly battling that legacy software and just waiting for tiered collaboration reviews. But in the AI-assisted workflow proposed by researchers at MIT, this entire tedious pipeline is compressed into mere hours.
When you compare the traditional legacy pipeline to the new way of doing things, the difference is night and day. The old way, writing legacy code, getting office feedback, subgroup feedback, convener feedback, is a remarkably slow, error-prone cycle. And those feedback loops take so long because they involve heavy, bureaucratic reviews, endless revisions, and waiting weeks for a committee to approve a tiny change in the methodology. But then you look at the interactive workflow powered by an AI agent, specifically Claude, equipped with old papers, review context, and data. This streamlined loop completely bypasses the bureaucratic backlog, bringing a physicist from raw data to a publication-ready result in roughly 3 hours.
Moving on to part 2, meet the JFC framework. JFC stands for just Furnish Context, and it's the engine making this whole revolution possible. See, JFC doesn't just write a massive script all at once. It breaks down the entire research task sequentially. It operates a lot like a graduate student progressing through their thesis research over several years, but done at lightning speed. First is strategy, where the AI maps out exactly what to measure and how to approach it. Second is exploration, which is essentially doing deep data reconnaissance to understand what it's working with. Third is processing, where it gets into the weeds of implementing event selection and background estimation. And finally, inference, where the complex statistical models are built and evaluated. Structurally, the entire framework is overseen by an orchestrator agent right at the top. Now, the orchestrator never actually executes code itself. Instead, it delegates tasks to specialized subagents across those sequential phases we just talked about. It keeps the complex methodology completely organized. And this is absolutely crucial, because if you feed a large language model too much complex physics data at once, its context window gets totally overwhelmed. It might start hallucinating or lose track of the core objective. By delegating step by step, the orchestrator ensures the AI stays perfectly on track.
But you might be wondering, how does the AI actually know how to do physics? Well, it uses something called Sci-tree RAG. The AI isn't just randomly guessing or relying on general internet knowledge. It actively queries a massive database of published experimental papers from historical particle collider experiments like ALEPH and DELPHI. It meticulously reads past literature to understand complex conventions, like how to properly design an event selection procedure or evaluate highly specific systematic uncertainties. This process grounds the AI's work firmly in established, real-world experimental practice.
Which brings us to part 3, a team of AI agents. Because let's be real, execution is only half the battle, right? In a real collaboration, results are rigorously and repeatedly reviewed. Well, JFC automates this too. Think of this multi-agent review process almost like an Ocean's 11 crew, where everyone has a highly specific, specialized job to pull off the perfect analysis. The physics reviewer acts as an external referee, purely checking the scientific merit of the work. The critical reviewer acts as the internal stickler, going through a punishing 14-point checklist for figure labels and methodology compliance. The constructive reviewer focuses purely on suggesting improvements and alternative approaches. And finally, the arbiter synthesizes all of these diverse findings into one final judgment. The really crucial point to understand here is that this review process is strictly binding. The arbiter looks at all the feedback and issues a firm verdict: pass, iterate, or escalate. If it says iterate, the system is thrown right back into a closed-loop revision cycle. The analysis literally cannot proceed to the next phase until all the AI reviewers have signed off and the arbiter finally issues a pass. It is an incredibly rigid structure. Human scientists don't even see the analysis until the AI has thoroughly and repeatedly checked its own work.
Part 4. The Human Unblinding Gate. Naturally, looking at all this autonomous automation, a major question pops up. When do the humans actually step in? Is the AI just out there publishing papers all by itself? To address the obvious sci-fi concern of AI taking over, the JFC framework implements a mandatory hard stop. The authors of the paper make this explicitly clear. While the AI handles the tedious implementation, humans remain the absolute, ultimate gatekeepers of the scientific data. The decision to examine the real, final data, a process called unblinding, is a profound judgment call that cannot and absolutely will not be automated. So, here is how that carefully structured unblinding protocol works in practice. First, the AI runs everything on expected, simulated results, which is often called an Asimov dataset. This is essentially a dummy dataset used so the AI doesn't accidentally peek at the real universe's answers before its methodology is completely verified. Then, it's allowed a partial unblinding on just 10% of the real data to make absolutely sure there are no catastrophic code errors. Next comes the human approval gate. It is exactly like a strict professor refusing to reveal the final exam answers until they have personally verified that a student's methodology is absolutely perfect down to the final equation. Only after a human physically clicks approve does the system proceed to step 4, the full unblinding on the complete dataset. And finally, Part 5, the future of research.
So, what does this actually mean for the field going forward? Because again, this isn't speculative, it is happening right now. Just look at these actual proven results generated by the framework. The AI successfully replicated a Higgs boson measurement using open data from the massive CMS experiment in just 6 hours and 30 minutes. It measured the Z-line shape from the ALEPH historical collider in under 5 hours. It measured the Lund jet plane density using DELPHI data in about 7 hours. We're talking about incredibly complex, multi-layered particle physics measurements that historically took years, literally years of a physicist's life, fully completed in roughly 5 to 7 hours.
But the ultimate thesis of this research is deeply optimistic. It states, rather than replacing physicists, these tools promise to offload the repetitive technical burden of analysis, code development. You see, AI is here to unburden scientists. It's here to give them their incredibly valuable time back, not to take their jobs. The implications here are just profound. First off, we can totally rethink graduate training. Instead of students spending their prime years just learning software engineering and writing boilerplate code, they can focus on actual physical intuition and high-level experimental design. Second, we can finally unlock massive legacy datasets. There are literally terabytes of old data from past colliders just gathering dust in archives right now. AI can now systematically comb through them at lightning speed, looking for missed anomalies or brand new discoveries. And third, this will drastically expedite those exhaustive collaboration reviews.
Ultimately, the physicist's role shifts from being a manual implementer to an architect and a critic. High-level thinking, asking creative questions, designing the analysis, and exercising expert physical reasoning, that will become the primary focus across all levels of academia, from the newest grad student all the way up to the tenured professor.
Which leaves us with a truly exciting prospect to end on. If we compress years of tedious coding into mere hours, we aren't just saving time, we are unlocking human potential. With the technical bottleneck finally removed, what incredible breakthroughs will human scientists achieve with all this newfound time to just think? I hope this explainer has given you a fascinating glimpse into the very near future of scientific discovery. Thanks so much for learning with me today.